First, I explain about Kerr-cat qubits. The basis of a Kerr-cat qubit is these two coherent states, and they are almost orthogonal to each other for large alpha, and they're eigenstates of hat A. So these coherent states are resistant to single photon loss, and bit flip errors can be suppressed exponentially with alpha squared. And this nature is called bias noise. Thanks to the nature of bias noise, the number of qubits needed for quantum error corrections can be smaller. So Kerr-cat qubits are a promising candidate for fault-tolerant quantum computers. And this is why Kerr-cat qubits are actively studied. And these are a few examples. And a typical coupling between Kerr-cat qubits is a ZZ coupling. And this ZZ coupling can be utilized for an RZZ gate, ZZ rotation. And operator of RZZ gate is defined here. And this RZZ gate is one of the entangling gates. However, if we cannot switch off the ZZ coupling, there occurs unnecessary RZZ gates due to the residual coupling called ZZ crosstalk. When residual couplings remain, even if we want to apply a single qubit gate here, some unwanted effects propagate to the neighboring qubits. So we cannot do local operations. Moreover, even if we want to operate, we want to do two independent single qubit gates here, they may affect each other. So we cannot do independent operations. In this way, due to the residual coupling, errors spread, and crosstalk errors are difficult to remove by quantum error corrections. So in order to build a large-scale quantum computer, we have to make a circuit with small residual couplings. In other systems, such as transmons, tunable couplers have been used to suppress unwanted residual couplings. For Kerr-cat qubits, in this paper, I and the other authors proposed tunable couplers for Kerr-cat qubits. But as you see, these circuits are a little complicated with two couplers for two Kerr-cat qubits. So here we propose a more simpler circuit with a single tunable coupler for Kerr-cat qubits. Our circuit performs better than the previous one. Before I explain the ZZ coupling between Kerr-cat qubits, let me explain a ZZ coupling of a diagonalized 2-qubit Hamiltonian. And this is a diagonalized 2-qubit Hamiltonian. E is the eigenenergy and psi is the eigenstate. And this Hamiltonian can be rewritten like this. And this theta given by this is ZZ coupling strength. our strategy to cancel ZZ coupling is to make the 4 eigenstates quadruply degenerate by making 4 eigenenergies equal. In this case, not only theta GZ, but also theta GI and theta IZ are equal to 0. And we define 4 logical states as the quadruply degenerate eigenstates. On the other hand, when the degeneracy is partially lifted, we can switch on the ZZ coupling. And this is a schematic of ZZ control, ZZ coupling control. From time 0 to TG get time, the ZZ coupling is on, and otherwise ZZ coupling is off. So from t equals 0 to TG, the degeneracy is partially lifted, but in other times, the 4 eigenstates are quadruply degenerate. We prepare the initial state as the superposition states of 4 logical states, and the system time evolves unitarily. And because of these conditions, we can apply an RZZ gate. Here, the small theta is a global phase, and capital theta is the ZZ rotation angle. Now, let me explain our system. And this is a Kerr parametric oscillator 1, and this is a Kerr parametric oscillator 2, and this is a tunable coupler. And they're capacitively coupled, and the total Hamiltonian is given by this. And this is a Hamiltonian of KPOJ, and here KJ is the cardinality of a KPO, and P is the parametric derived amplitude. And the Hamiltonian here is written in a rotating frame at frequency of omega p over 2. Omega p is the parametric derived frequency, and because we are in a rotating frame, here appears a detuning of omega lambda from omega p over 2. Omega lambda is the resonance frequency, and this is a Hamiltonian of coupler, and coupler is not parametrically driven, so here P does not appear in this Hamiltonian. And this is a interaction Hamiltonian between the subsystems. G is the coupling strength. The total Hamiltonian can be written like this, and this HZZ is a ZZ coupling Hamiltonian between Kerr-cat qubits, and this HX is a Hamiltonian for x-axis rotations. For now, we don't want to apply an RX gates, so we set this part 0, and this hx disappears. And we also set these parameters small so that we can treat HZZ as a perturbation. So in the zeroth order of perturbation, we have these 4 eigenstates of H0, and these 4 states are quadruply degenerate. And the eigenenergy is given by this. And as I said, this HZZ is treated as a perturbation, and in the first order of perturbation, 4 eigenenergies and ZZ coupling strengths are calculated like this. And by controlling the parameters appearing here, we can switch on and off the ZZ coupling. The parameters appearing here can be controlled through phi C bias shielder. And here, the left-hand side is the dimensionless magnetic flux, and it is defined by this magnetic flux is divided by reduced flux quantum. And we decompose this dimensionless magnetic flux into 2 parts, parametric pump part and a bias part. This bias part can control the parameters here. As we can see, at these 2 points, we have theta TZ equal to 0.0 kilohertz. So we can switch off the ZZ coupling. The previous explanation is based on a perturbation theory. So if the ZZ coupling is really switched off, we did numerical calculations. We prepared initial state as a superposition of 4 logical states, and we checked whether or not the time evolved state changes from the initial state or not. Here is the result. As we can see, the infidelity is very low and about 4 orders of magnitude smaller than the previous case. In addition, we numerically calculated RZZ gate infidelity. At this time, to apply an RZZ gate, we switch on ZZ coupling by this parameter schedule. And we do not want to apply an Rx gate. This part is set to 0. So there are 2 equations to satisfy. And from this equation, the detuning schedule is determined like this. And from this equation, the detuning schedule of KPOJ is determined like this. And the result is here. Green circles are obtained by satisfying both of these 2 equations. But as we can see, the change of delta J is small compared to delta change of delta C. So we also calculated the case in which delta J is set constant. Even in this case, we have small gate infidelity, as you can see from the red diamonds here. So in conclusion, we proposed a coupling scheme to control the ZZ coupling between Kerr-cat qubits using a single tunable resonator. And we can suppress residual ZZ coupling between Kerr-cat qubits, as we saw in numerical calculations. And this circuit is simpler and has better performance than the previous work. And as an artwork, integrating our scheme with surface codes for biased noise may be an interesting future work. Thank you for listening.
Questions? Okay, maybe I can ask one question. What's the advantage of Kerr-cat qubit compared to transmons or fluxonium qubit?
Thank you. As you can see, Kerr-cat qubits are resistant to single photon loss. So bit-free errors are suppressed exponentially with alpha squared. And thanks to this biased noise nature, for quantum error corrections, we almost need to focus on phase flip errors. So the number of qubits needed for error corrections can be smaller than the transmon or fluxonium case. So the overhead for quantum error corrections can be small. So this is an advantage of Kerr-cat qubits.
Yeah, for example, for surface code, you only care about, you only cancel one of the errors. The other error is already taken care of.
Yes.
Okay. Thank you very much. Any other question? Let's thank the speaker again.
Thank you.